So, welcome to lecture series on advanced linear algebra. We have discussed what is eigenvalue, eigenvector, diagonalization of the operator. We also discussed the meaning of annihilating polynomial of a finite of a linear operator defined over finite dimensional vector space, or annihilating polynomial of for a n cross n matrix defined over the field. We have also defined what is the meaning of minimal polynomials, characteristic polynomials. We have seen that the least degree monic generator of the ideals of all the polynomials which annihilates an operator t, that is basically minimal polynomials for the operator t. Apart from the minimal polynomials, there exists a polynomial, this is called the characteristic polynomial. We have also defined what is that. Cayley has given, basically Cayley as well as Hamilton, both of them has given one nice results, that every linear operator defined on a finite dimensional vector space is a root of its characteristic polynomials. So, that is basically Cayley-Hamilton theorems. So, let me state what is the statement of the theorems. Let T be a linear operator on a finite dimensional vector space V, which is defined over a field, say capital F. Similarly, I can also say that let A be an n cross n matrix over a field capital F. Let Fx denote the characteristic polynomial. Is take polynomial of t, or I can say A. I will also explain the meaning why I am saying that t or A. Then f of t equal to 0 or f of A equal to 0. In fact, it says that minimal polynomial of t or A divides characteristic polynomial. Take polynomial of t or A. Okay. So, statement of the theorem is like this, say T be a linear operator defined over a finite dimensional vector space V. Say for example, the dimension of the V is say n, and let A be a square matrix over the field capital F. For if I consider V is a finite dimension of dimension n, here I will consider A is a n cross n matrix. Let F denote the characteristic polynomial of T or A. Then f of t or f of A equal to 0. F of t equal to 0, I mean, or if you consider instead of t matrix A, then f of A equal to 0. So, this statement says that if the minimal polynomial of t or A is suppose p, then certainly P will divides F, because according to the definition of the minimal polynomial and characteristic polynomials, minimal polynomial is the least degree monic generator of the ideals of all the polynomials from the Fx, then field of polynomials Fx, which will basically annihilate the operator T or matrix A. So, since F is also annihilating, then definitely F will be multiple of P. So, that is why I am saying that in fact the minimal polynomial divides characteristic polynomial of the T or A, please. There are different ways to one can prove this result, please. I have used the word that T be linear operator on a finite dimensional vector space V, or have taken A is a square matrix over the field, say capital F. Already I have established the results. If you remember, any finite dimensional vector space is isomorphic to corresponding, say, n dimensional array space, that is n tuple space. If I consider V is a finite dimensional dimension n, then V is isomorphic to Fn, or f of V is isomorphic to also Fn cross 1, if V is a finite dimensional of dimension n. Now, since T is a linear operator defined over finite dimensional vector space V, I can consider standard order basis on V. Then based on, if I consider V is basically say, since it is isomorphic, I can say that V is basically say Fn, then we can have a matrix representation of the T with respect to standard order basis on that space. And that, if I say that is basically my capital A, then talking characteristic of the operator T, talking characteristic of the matrix A, both are same, please. So, instead of operator, I will talk basically proof for the matrix, square matrix A, please. Okay. So, given A is an n cross n matrix over the field capital F. According to definition of the characteristic polynomials, so I can say characteristic polynomial of A is basically determinant of x I minus A, or one can write also minus 1 to the power n to A minus x I, both are same, please, because from the definition of the determinant of the matrix, these two are same statement, please. Given, it is also given to us Fx equal to your determinant of x I minus A, this ones. So, since the characteristic polynomial for the matrix A, where A is n cross n matrix, will be a polynomial in x of degree at the most n. So, let Fx is equal to A naught plus A 1 x plus A 2 x square plus A n minus 1 x to the power n minus 1 plus x to the power n, because it is a monic polynomials. So, the coefficient of highest power must be equal to 1. So, that is why Fx equal to of this structure, please. If you recall the definition or some property of the adjoint matrix, let Bx denote adjoint of x I minus A. Then we know from the classical theory adjoint of a matrix okay, x I minus this matrix A, and adjoint of x I minus A will be equal to determinant of x I minus A into identity matrix. This is the classical results we know. So, I have considered here B x equal to adjoint of x I minus A. But what is this? So, to have a quick idea about this, let me also parallelly take some examples to let A equal to, let me consider here A11, A12, A13, A21, A22, A23, A31, A32, A33. This is a matrix space. So, if I consider adjoint of, say, I will take A minus x I, because minus 1 to the power then 3 I have to multiply it. So, this is equal to, let me see what is this, this is equal to, so I have to take the cofactors of this A minus x I mean we have to take the cofactors for the each of the A11, A12, A13 all these things, and then take the transpose of that is basically adjoint of A minus x I, that is the definition of the adjoint matrix we have learned. So, based on that if I proceed it, see here I will have basically what I will have I can write simply determinants of adjoint matrix. So, let me write this one please. So, A11 minus x, A12, A13, A21, A22 minus x, A23, A31, A32 and A33 minus x. Okay. So, I will have parallelly like these things. So, now this is basically I have to take the adjoint of this matrix space. Okay. So, I have to see what is the cofactor of A 1 minus 1. So, cofactor of this quantity will be what? Cofactor of this will be determinant of this matrix. So, I will have A22 minus x into A33 minus x minus your A23 into A32. So, the cofactor will be cofactor of B11 because this is a B matrix. If I consider this one, then B11 will be this minor multiply into minus 1 to the power 1 plus 1, that is the cofactor please. So, anyhow I am getting this is a polynomial in x of degree 2. Similarly, if I go for the A12, I will have polynomial of degree at the most, in that case I will have polynomial degree only x, other case is also x. So, I will have the cofactors of each B I j will be basically polynomial of degree at the most n place. Then each entry B I j of B matrix will be a polynomial in x of degree at the most n minus 1 place, because when I consider A is equal to 3 by 3 matrix, I am getting the maximum degree of this polynomial is 2 only. So, one can rewrite. So, this implies B x can be written as B x equal to, I will have x to the power n minus 1 B n minus 1 plus x to the power n minus 2 B n minus 2 plus x into B 1 and plus B naught, where each B I equal to 0 to n minus 1 is n cross n matrix over the field capital F. So, I see that the adjoint of the x I minus A is basically n cross n matrix written like this P x. So, if I say this is star, so this implies x I minus A into B x equal to determinant of x I minus A into I. Okay. So, this is like this thing. So, this implies I will have x I minus A matrix into, I will write down B x equal to x to the power n minus 1 B n minus 1 plus x to the power n minus 2 B n minus 2 plus B 1 x into B n plus your B naught. So, this is equal to x to the power n plus A n minus 1 x to the power n minus 1 plus A 1 x plus A naught whole into identity matrix, because determinant of x I minus A equal to this polynomial place. So, that is why I have written this one. Now, find out the coefficient of different power of x. So, let us first find out the coefficient of x to the power n. What is this? So, on the both side if I have and compare, then I will have, see this side is I will have only B n minus 1. So, this will be equal to certainly identity matrix, because the coefficient of x to the power n equal to, this is only 1. So, 1 into identity matrix this one place. So, the first equation like this thing is. Now, coefficient of x to the power n minus 1. So, coefficient of x to the power n minus 1 I am getting as minus A B n minus 1 and plus B n minus 2. So, this is equal to, I will have A n minus 1 into I. Okay. Then similarly, coefficient x to the n minus 2, I will have what? Minus A B n minus 2 and plus B n minus 3 equal to, I will have A n minus 2 into again I. So, if I keep on doing like this, coefficient of x will be what? Coefficient of x will be, here I am getting minus A B naught, coefficient of x, sorry, then minus A B 1 and plus B naught. So, this will be equal to then A 1 into x, and I mean coefficient of x to the power 0, that is equal to how much? Minus A B naught. So, this is equal to A naught into I. Now, multiply, see the first equation by, so if I multiply this one by A to the power n, and this is say A to the power n minus 1, and this is say multiplied by A, and this is multiplying by a to the power 0. So, multiplying, so this is, say, let us consider the first equation, this is my second equations, and this is third equations, and this will be, say, nth equations, n plus 1 equation. So, multiplying a to the power n, a to the power n minus 1, and so a to the power 0 to equation 1, 2 and n plus 1, and adding column wise, we have what do we have? See, if I multiply this ones, a to the power n, and this is again a to the power n this side. So, this is I am multiplying from the left side, please, multiplying from left side. So, I will have a to the power n bn, and this to the power also a to the power n bn. So, it will cancel out, this will all cancel out, this will all cancel out, please. So, it will be basically we have 0 equal to a to the power n plus a n minus 1 a to the power n minus 1 plus a 1 a plus a naught into I. So, this implies that f of a equal to 0. So, this is the Cayley-Hamilton theorem, please. Okay. So, we can take some examples. So, let me take an examples. Let T be a linear operator defined by T of x equal to x 2 plus x 4, comma x 1 plus x 3, comma x 2 plus x 4, comma x 1 plus x 3 transpose. So, that its characteristic polynomial is x square into x square minus 4. Okay. I mean to say, I have to show that a to the power 2 and a to the power 2 minus 4 equal to 0. To prove this one, I have to immediately translate this operator into the corresponding matrix form. So, consider the standard order basis E1, E2, E3, E4 where your E1 equal to say 1 0 0 0 transpose, E2 is equal to 0 1 0 0 transpose, and so on, please. So, we see that T of E1 equal to what? T of E1 equal to I am getting say 0 1 0 1 transpose. So, if I write down this column vector in terms of E1, E2, E3, E4, this implies that the T1, the coordinate matrix of T1 with respect to this order basis say B will be equal to your 0 1 0 1 transpose. Similarly, if I go for the T2 will be equal to 1 0 1 0 1 0 1 0 transpose, and this implies T2 coordinate matrix of T with respect to B will be, again I can say 1 0 1 0 please, and similarly you can see that T3 coordinate matrix of T3 with respect to B will be 0 1 0 1, and Te4 will be 1 0 1 0. So, this one. So, this implies the matrix representation of T with respect to order basis B will be equal to 0 1 0 1 1 0 1 0 0 1 0 1 1 0 1 0. So, this is the matrix please. Okay. So, one can find out the characteristic polynomials. So, characteristic polynomials will be, suppose this is equal to say capital A, there will be determinant of x I minus A or minus 1 to the power 4 into determinant of A minus x I. So, if I do it, it will basically I can say minus x 1 0 1 1 minus x 1 0 0 1 minus x is the 1, and then it will be 1 0 1 and minus x. So, determinant of this quantity. This you will see that it is nothing x square into your will have, you can check, it will be x square minus 4. So, this thing we can check it. So, leave it as a homework, this one. But this thing I will show that, I will show by showing that calculating different power of A and showing that a square into a square minus 4 I equal to 0. Since this is a matrix of 4 by 4, so I need a characteristic polynomial has to be 4 degree polynomial please. So, let me quickly calculate what is a square please. We have A equal to 0 1 0 1 1 0 1 0 0 1 0 1 and 1 0 1 0. So, a square will be this into again 0 1 0 1 1 0 1 0 0 1 0 1 and 1 0 1 and 0 please. So, if you multiply these two matrix, I will have what? This will have basically. So, first entry will be 2 because 0 1 0 1, okay. Second entry will be 0, third entry will see that 2, fourth one 0, second this will be 0 and this will be again 2, second column will be 2 and then third one will be here 0, it will be again 2. So, you can check it, next row will be 2 0 2 0 0 2 0 2. See, if I go for AQ equal to what? 2 0 2 0 0 2 0 2 2 0 2 0 0 2 0 2. This when you multiplying to your 0 1 0 1 1 0 and 1 0 0 1 0 1 1 0 and 1 0. If I do it, I am getting what? Okay, first multiplying this one, this is first one 0 0. Okay, so here I am getting the first entry is 0. What about second one? This is 2, 0, again 2. So, I will have 4. Third one we will see that 0, fourth one will have 4. So, again second row 0, 2, yeah, we will have 4, 0, we will see that 4, 0 and 0, 4, 0, 4, 4, 0, 4, 0. So, I am getting AQ is equal to, this is equal to 4 times basically your A. So, AQ minus 4A equal to 0. So, this implies that A into S square minus 4 equal to 0. So, Px is equal to x into x square minus 4, this has to be the minimal polynomial, is minimal polynomial of A. For we can check it again, what about a to the power 4? A to the power 4 will be, I can simply say that 0, 4, 0, 4, 4, 0, 4, 0, 0, 4, 0, 4, 4, 0 and 4, 0. Yeah. So, when I multiply this into 0, 1, 0, 1, 1, 0, 1, 0, 0, 1, 0, 1, 1, 0, 1, 0, what I am getting? I am getting, so first entry will be 8, second will be 0, then 8, 0, 0, 8, 0, 8, 8, 0, 8, 0, 0, 8, 0, 8. So, I will have matrix like this thing. So, this is equal to, okay, so S square equal to this quantity. So, I can take the common 4. So, it will be 4 into S square. So, this implies a to the power 4 minus 4 S square equal to 0. So, this implies f is equal to x to the power 4 minus 4 x square as characteristic polynomial of A. And I also see that because the 4 degree polynomials and x into x square minus 4 equal to Px, this divides Fx equal to x to the power 4 minus 4 x square. So, you see that the minimal polynomial divides characteristic polynomial also. Characteristic polynomial is equal to, this is equal to x square into x square minus 4. So, I will have x is repeating, x equal to 0, 0 and x equal to 2 and minus 2. So, I will define to another terminology, that is called algebraic multiplicity and geometric multiplicity. What is algebraic multiplicity? In general, if f of x is written like this, say let us consider x minus c1 power say d1 into x minus c2 power d2 and say x minus ck power dk, where c1, c2, ck are the distinct eigenvalues, then di is known as algebraic multiplicity. Multiplicity of eigenvalue that is your Ci. Let Wi denote the null space of your A minus Cii. If I consider this matrix, then that is basically eigenspace associated to the eigenvalue Ci, then dimension of Wi is called as geometric multiplicity of eigenvalue Ci. So, in this example x equal to 0 having x equal to 2 and minus 2 having geometric multiplicity is 1, but what about the geometric multiplicity of x equal to 0? So, in that case I have to basically calculate the rank of this matrix here, because x equal to 0. So, this rank of this matrix here I have to calculate, please, because I can see it here A is equal to the matrix is 0 1 0 1. So, it is repeated. So, only 2 linearly independent rows will be there. So, therefore, definitely rank of the your eigenvalue x equal to 0 here in this case will be 2. So, since rank is 2, so null space of the A minus 0 I will be dimension 2. So, definitely geometric multiplicity for the eigenvalue x equal to 0 will be again 2, please. So, I hope you have understood this concept of Cayley-Hamilton theorems and the concept of geometric multiplicity, algebraic multiplicity.